Hey guys, welcome back to my implementation series. So in the last video, I'd covered the scan to map algorithm. In this video, which will be the final video of the implementation series, I'll go over point 10 and 11. So point 10 is the point cloud deskew mode, and point 11 is the error state Kalman filter mode with the IKD tree map backend. So in point 11, the IKD tree map backend and the error state Kalman filter were used in the FastLiO 2 paper, and this is a custom implementation of that. So let's start with point number 10. So what is the purpose of deskewing point clouds? The reason we want to deskew point clouds is because when we get point clouds, and this deskewed version will actually go into the error state Kalman filter mode, but when a scan happens, depending on whether points in the point cloud are scanned at the beginning of the scan or the end of the scan or the middle of the scan, um, the robot pose may be different at the time of the scan, right? So if we don't correct for the robot pose, what could happen is walls could smear, and that would not be helpful for downstream algorithms that consume that point cloud. So we want to ensure that all of the points from the point cloud are essentially coming from the same frame, right? So if a rover is turning mid-scan, we want to essentially take all the point clouds that are coming from the beginning of the or the middle of the scan and push them to the frame of the rover at the end of the scan. And that's what this deskew mode is doing. It's taking all of the different points of the point cloud, and depending on what time during the scan the point was registered, it's forwarding it to the end frame, right? Essentially the end pose of the robot at the end of the scan. So we'll go over that. So let's go over this launch file, right? So basically, and it's doing this using IMU. So the IMU measurements are coming in at a much higher frequency than the LiDAR scans, right? So mid-scan, we're going to get a bunch of different IMU measurements. So we can take points that are registered at the beginning of the scan or middle of the scan and use the rotation measurements that we get from the IMU in order to kind of push those points to the frame at the end of the scan, right? Represent those points in terms of the frame of the rover, um, or you could say the frame of the base link of the rover, the center of the rover at the end of the LiDAR scan. So let's take a look at this launch file. I'm not, again, going to go over the first point because we've already seen what happens when we launch the LiveVox ROS driver. So we'll take a look at this launch file, scan to map, deskew, cost map, projection launch, right? So if we take a look at that, scan to map, deskew, cost map, projection launch here, the main module that we want to focus on is custom LiDAR deskew, right? So if you go to this particular package, custom LiDAR deskew, we can look at LiDAR deskew node.cpp, and we can look at the callback, right? So one call out here, if we look at this callback, right, the input topic that this is registered to, if we go to the config, is actually custom points for deskew. So you'll see that if you go through the FastLiO preprocess, in addition to the custom points preprocessed and custom points for nav2, we're also publishing points for deskew from the preprocess module, right? So um, this is being ingested into this deskew node, right? So let's go back to the cloud callback. So in the cloud callback, the main thing you want to focus on is basically, if we go down here, collecting the IMU samples. So you probably want to look at how the IMU samples are being collected in a buffer, um, and also the deskew cloud rotation only. So this is the main function that actually performs the deskew. So we can go in there, and within that function, the main pieces that are actually doing the deskewing are integrate rotation and then interpolate rotation, which captures all the point clouds at the end of the scan, right? And those two functions are in IMU integrator.cpp. So you can go through integrate and interpolate rotation, how every point in the point cloud is being kind of rotated to the end of the scan, right? So that the entire point cloud is captured in one frame, specifically the frame of the rover at the end of the LiDAR scan, right? This avoids, as I said, any smearing on walls or corners. So yeah, so that is what this particular node is doing. So if we go back to the launch file, everything else is pretty much the same. as we had it before, we have the scan to map node, we have um, Livox Cloud to Scan. It's exactly what was there in the scan to map launch file as well. So the only difference is that dskew node, right, which is essentially pushing the points from the point cloud to the end of the scan. Okay. Now on the pi is the same. It's using the same cost map projection nav2 launch, right? So that is point 10. So now let's move on to point 11. All right, so now we'll go over the error state Kalman filter and the IKD tree. First, I'll go over the error state Kalman filter. So the purpose of the error state Kalman filter, it uses this idea that the rate at which IMU samples come in is much higher than the rate at which LiDAR comes in, right? So LiDAR is very accurate in terms of telling you about the geometry of a room, right? It knows where the obstacles are, and it's very good at kind of telling you how your rover has moved based on how the geometry is changing around the rover. The IMU is very good at rotation measurements, right? And the rate at which the IMU samples are coming in are very high. So you get a very fast stream of data, which may not be as accurate as what LiDAR can do, because LiDAR has an understanding of the geometry of the room. But LiDAR is slow. So if you just update your pose, when you get LiDAR scans, you'll have these wild jumps in pose. So what the error state Kalman filter is trying to do is it's trying to combine these two concepts where there's a prior estimate of the pose of the rover based on the IMU samples that come in between LiDAR samples, and with a certain degree of covariance. And then when a LiDAR sample comes in, we estimate the pose correction, or what's called the error, between our prior estimate and where the rover actually is. And once we inject the error, we have to update our uncertainty measurement, our covariance, right? Because our uncertainty will change once the pose has been corrected. So that's essentially what's happening at a high level in the error state Kalman filter. We have these back and forth between the IMU samples that provide a prior and then the error correction done when we get a LiDAR scan. Right. So let's go through some of the code here. So we'll focus on this particular file, LIO EKF dskew cost map projection. So let's go there. Yeah. So if you look at this particular file, again, it's very similar to the other launch files. The main difference is essentially this custom LIO EKF node. It's also the input topic to this node, and also the input topic to the Livox Cloud to Scan node now is coming from the previous point. It's coming from that deskewed point cloud that we just talked about, right? So that we don't get any smearing or anything like that. And this algorithm can run more effectively that way. So now let's go into this custom LIO EKF package, right? And specifically the EKF node in there. So if you look inside the custom LIO EKF package, the source folder, you'll see a bunch of CPP files. Let's focus on the LIO EKF node. So in the LIO EKF node, we have the cloud callback, right? So the first part you really want to focus on here, there's some filtering that's being done. But the first part is run prediction. So this is what's called nominal state propagation and covariance propagation. So this is where the IMU samples are being used to generate that prior estimate of the robot pose. So we can go to run prediction. And there's predict state and covariance, right? So predict state and covariance comes from covariance propagation, I believe. So we can go in there. All right. So you can focus on this piece. This is essentially where over here propagate state and covariance, the nominal state propagation is happening. So the nominal state propagation is this idea of using the IMU samples to essentially estimate the pose of the rover between LiDAR scans so that when the next LiDAR scan comes in, we have a prior estimate with a certain degree of covariance, with a certain degree of uncertainty. Right. So this is where it's happening. Propagate state and covariance within predict state and covariance. Right. Now, if we move on from, we were at run prediction in the cloud callback. Yeah, sorry, right there, run prediction. If we move on from there, we can see run LiDAR update. So this is where, this is what happens when the point cloud comes in, right? Remember, this is the cloud callback. So when the cloud callback comes in, we've been saving these IMU measurements. So you might say, okay, the run prediction should be happening not just when a point cloud comes in, right? It should be happening like between two point clouds. And it does, because before we move on to the LiDAR update, I'll just clarify this, because there's an IMU callback as well. There's an IMU callback which is essentially saving the IMU messages in a buffer, and whatever's been saved is just being used for nominal state propagation when we get the point cloud in the cloud callback. So now we can move on to, okay, we have this prediction, we have this prior estimate of our rover based on the IMU sample. So now we look at the LiDAR update, right? We have run LiDAR update over here. That's coming from here, and apply iterated LiDAR update, I believe is coming from iterated LiDAR update right here. So this is where the LiDAR update is actually happening. So you can see the error state difference. We're building the normal equations. So all of this will make sense if you actually go through the details of the error state Kalman filter algorithm, how it's used with LiDAR inertial odometry, right? So all of this is happening, and the error here is being injected. So this is where the pose correction is happening. We're taking our current prior estimate of the pose, and we're essentially injecting the correction to update it. Um, so that's what's happening over there. And we're also updating our covariance matrix as well. So this is the LiDAR update part of the EKF node, right? So if we go back to, let's go back to our cloud callback, right? Okay, run prediction, LiDAR update, right? So we've updated it. Then over here, we update our map because we've gotten these new points, right? So we want to update our map as well after we correct for our pose. So we do that as well, and then we publish our odometry, right? Over here. So essentially that's what's happening in the cloud callback. We're trying to estimate the pose of the rover using first the nominal state propagation from the IMU samples doing run prediction, and then applying that iterated LiDAR update. So get the one, when we get the current LiDAR scan, we have this prior estimate, and then we're essentially trying to estimate the error, what we call the error, or the pose correction, and then inject that into the current prior. And that'll give us our odometry estimate, which we'll then publish on the nav2 odom topic. So if you go back to the launch file, you'll see that the odom topic is nav2 odom, right? So that it can be used in the nav2 stack. All right, so that's what's happening over here. Now let's move on to the IKD tree. All right, let's talk about the IKD tree data structure and how it's used. So the purpose of this lies in the fact that during the LiDAR update phase of the EKF, we have to calculate what's called the point-to-plane residual. So if you remember from the scan to map phase, we used to find like nearest neighbors to every point in the point cloud, and then we used to find the orthogonal distance to the local plane created by those nearest neighbors. So there is an aspect of that in the EKF algorithm as well. And so there's a lot of nearest neighbor calls that are made during the LiDAR update phase, right? And so we need to ensure that nearest neighbors is nearest neighbors to points in the local map is very efficient. And earlier we would do it in the scan to map algorithm with a KD tree. The problem is that in our case, we're adding points to this tree pretty frequently because every time we correct pose, we update the map. So if we see some new points, we see some new geometry, we need to add that to the map. And we're also deleting points because we're essentially cropping outside a box that encapsulates a rover. So we're only keeping points in our local map that are in a box around our rover, right? So that we don't keep very distant points and the map doesn't grow too much. So that to keep searches efficient, essentially. So there's a lot of insertion and deletion going on. So in a traditional, the difference between an IKD tree and a KD tree, the reason you would want to use an IKD tree over a KD tree, in a nutshell, would be because if you're doing a lot of insertions and deletions, your tree is not static. And so if you use a traditional KD tree, it could become unbalanced very quickly, and then you would give up the efficiency you get by using a tree-like data structure for nearest neighbor search. So an IKD tree remains fairly balanced, and so gives you very efficient runtime, even if you're doing a lot of insertion and deletion. And that's the main reason to use an IKD tree over a KD tree. So that's why we're using this data structure. Now, to focus, if you want to focus on the areas of the code where this is actually being used, go back into the LIO EKF node file and start at configure map backend. So this is where the map backend is essentially configured, right? So if you look at the config, LIO EKF YAML under the config folder, the backend type is IKD tree. So over here, we set if the backend type is IKD tree, we create essentially a IKD tree backend object called map backend, right? So you can look through the EKF-LIO EKF node wherever map backend is used. So map backend is used in multiple places, right? So for active size, over here we're getting the active points, we're deleting outside box and so on, right? And the file you want to refer to, like if you find like you want to figure out what get all active points does, for instance, right? Or you want to figure out how deletion is being done or insertion is being done. What I would recommend doing is going into this other package. Let me find it here, custom IKD tree backend. And this map backend is essentially an object of the type IKD tree backend right here. So you can essentially focus on this particular class, and you can focus on the methods in that class, right? So over here, we will have like get all active points, for instance, right? Get all active points, and then there's deletion as well being done in here. So delete outside box. So this is essentially delete outside box is essentially the method that's deleting outside the box containing our rover, right? So everything, all the points outside that box can get deleted. So this is what's being used when we want to do something like that, right? So there's also insertion method. So you can look through this map backend to get an understanding of the functionality of the IKD tree. But in a nutshell, what the IKD tree is doing is it's keeping our nearest neighbor search efficient, even after many insertions and deletions. So that's what's happening. So now I'll show you if everything is running, what topics we actually see. So let's do that next. All right, so now I'm running point 11 on the Jetson to show you the topic list, right? What's actually being published by the code base that we just reviewed. So the first point here is the LiveVox ROS driver. So on this terminal, I'm running the LiveVox ROS driver, and that's, as you know, publishing LiveVox LiDAR and LiveVox IMU messages. And then on this terminal, I'm running the second launch file, which actually launches the EKF node right over here. So that's what's running. Now let's look at the topic list. So if I look at the topic list here, there's some interesting topics here. One is diagnostics. So LIO EKF diagnostics is a very useful topic. It kind of tells you what's happening with the EKF algorithm. So you can essentially echo that, and it's very useful for debugging. So it gives you a bunch of stats. So let me just show you that topic. So these are a bunch of stats coming from the EKF algorithm, right? Whether the prediction was a success, how many local map points there were before updates, what was the mean residual, the max residual. So if these residuals are really, really high, you know that the algorithm isn't converging to an acceptable value. So the rover pose isn't being correctly estimated, right? For instance. So you can kind of use this to do debugging. You can look at the time it takes to do LiDAR updates or map updates to figure out if you're taking too much time. Because if you're taking too much time, then that won't really be great for the nav2 stack, because nav2 ODOM should be published at a particular rate, right? So you can use these values to kind of like debug. So that's what that's for. And then if we look at some other topics, there's a similar diagnostics topic for the DSQ. cloud as well. And there's also nav2 ODOM, of course, that's what's being published by the EKF algorithm, right? And you have some other topics that we expect, like the preprocess node is publishing points for DSKU, points for nav2, the upgraded cost map, the custom obstacle cloud is being published, right? So this is what's happening. Now, for the actual demo of the run, you can take a look at the overview video. So the autonomous navigation run in the overview video is essentially using point number 11 in the README. It's using this error state Kalman filter with the IKD tree that we just went through. So that is the final kind of custom algorithm that's used for autonomous navigation with nav2. So I hope you enjoyed this implementation series. That's all for this video. Thanks.